Good evening to all of you. My name is Ramesh Srinivasan. Now, we are going to learn how to mark the normal force in a free body diagram. See, the normal force is a contact force. As long as there is contact, it exists. If the contact breaks, there is no normal force. So let's say I put both my palms together and press it, there would be a normal force between these two. As the name suggests, normal is perpendicular to the surface. The normal here means that it is at right angles to the two plane surfaces in contact. So let us see the nature of this normal force. First of all, if there is say a floor, a flat floor, and I place a block of mass m here on it, I know that it is at rest. So, how do I draw the normal force for this? Let us find out let us draw the free body diagram for M. That is, we will isolate M from the surroundings and show it as a point mass. The most obvious force is the weight. All the earth pulls all bodies near it. So, that is the weight. The pull of the earth is the weight. So, that is Ng. Now, since the body is at rest and it cannot be at rest under the influence of one force, there must be another force. What is that other force? It must be applied by an external agency. So, the external agency is the floor and it applies a force N, the normal force, in the upward direction. Now, remember, this N and mg are not the action reaction pairs of the Newton's third law. If this is the floor, then the N by the block is applied on the floor this way. These two are action reaction pairs. The action reaction pair for this is on the earth. The earth applies a force mg on the mass m, and there is a force mg on the earth as well. Okay, since we are not studying the earth, we ignore that force. So, we have N is equal to mg. See the nature of the two forces, of the pair of forces. See, these are the two surfaces in contact. N on this surface is upward, N on this surface is downward. So, the normal force is a pushing force. One surface pushes another surface. Now, obviously, you will say if there are two surfaces and both of them push each other, they will separate. But they will not if there are other forces which ensure that the contact is not broken. That is the case here. Mg is acting and it ensures that the contact is not broken, and hence N and N keep acting. Now, the next thing is we could see, supposing we have a floor again and a block and another block. Let's say I will call this as M1 and M2. Let us draw the free body diagram for this. I will have M1G. There will be N1, the contact force. M2 will push M1 upward, N1. So that completes the free body diagram of M1. For M2, it will be M2G weight. For N corresponding to N1, there will be a reaction N1 by M1 on M2. Then there is the floor. The floor will exert a force N floor. I'll call that N floor. That is the free body diagram. If you draw the free body diagram of the floor, there will be an N floor downward, equal and opposite to this. So the agencies must be very clear. Who is applying the force? The agency manages. This agency has always to be external to a body. By Newton's second law, or rather by Newton's first law, every agency is external. No body can exert a force on itself. Okay. So these are the forces. Now, let us say we have a horizontal surface and we place two blocks side by side, almost touching each other. That is, I have a floor I have a horizontal floor. This is M1 and this is M2. This is the horizontal. This is a horizontal surface. If I place it like that, well, I know there will be M1G, there will be N1, there will be M2G, and there will be N2. Between these two surfaces, will there be a contact force? Is the question. The answer is no, because the normal force is a pushing force. The normal force is a pushing force. So this surface would push M1, M2 will push M1, M1 will push M2, and so the contact will be broken. So although it seems that they are touching each other, there is actually a gap, thin gap, and there will be no contact force in this case. Let us take another example. This was horizontal. Suppose you take an incline, and this is theta, and there is a block M like that. Let us draw the free body diagram of this. If you draw the free body diagram of this, I am showing this block as a point mass, and this is mg. Now we have to draw the normal force. The normal force is normal to the surfaces in contact. So it will be like this. This will be like this. So if I extend this like that, and this like that, this is theta, this angle would be theta. Why? Because in this right angle triangle, this plus this is 90 and this plus this is also 90. This is common, so this is theta, this is also theta. Now we need to resolve and find M1. Now there can be little confusion at this stage. See, supposing I can resolve N, I got N like that and Mg like that. So I could resolve N as N cos theta and N sin theta this way, or I could resolve Mg. This is Mg, this is N. So this is theta. I will have Mg cos theta here this way, and I will have Mg sin theta, orthogonal components, Mg cos theta and Mg sin theta. And so I can say N cos theta equal to Mg and N sin theta is the resultant force. Or I can say N is equal to Mg cos theta and Mg sin theta is Z. So there is a confusion here. How to resolve? So here you must not lose sight of the practical thing which is happening. This block, we are assuming that it is smooth. If let on the smooth surface, it will go down, it will accelerate downward. Now if you resolve it like this and say N cos theta is equal to Mg and N sin theta is the resultant force, this block is shooting like a rocket, yes? It is not happening. So this is wrong. So the correct thing to say is that N is equal to Mg cos theta and is accelerating down due to a force Mg sin theta. Now let us say there are two blocks placed touching each other on a smooth incline. Two blocks touching each other, M1 and M2. This is smooth and this is theta. So we know N1, the N1 would be M1G cos theta and N2 would be M2G cos theta. You would like to know what is the contact force between M1 and M2. So if you draw the free body diagram of M1, there will be, I am not showing M1G cos theta and N1, I am only showing the force along the incline. I have M1G sin theta, M2 would push M1, let me call that as N. Free body diagram for M2, M2G sin theta, M2G sin theta, and the M1 would push m2 backward. So this is how the forces are. Let us assume both of them are moving together with a common acceleration A. Yes, they are in contact because we have put n as non-zero. Obviously, they are in contact. So I can say m1g sine theta minus plus n is equal to m1a, and m2g sine theta minus n is equal to m2 into a. Correct? m2g sine theta minus n is equal to. Now if I add both of these, I will get m1 plus m2, n will cancel if I add these two. m1 plus m2 g sine theta is equal to m1 plus m2 into a. m1 plus m2 cancels and I get a as g sine theta. A as g sine theta. So if I put a as g sine theta in the first equation, m1g sine theta and m1g sine theta will cancel and I will get n equal to 0. Similarly in this also I will get n equal to 0, whichever equation I take. So even if you leave both the bodies, press them and put them in contact and leave it, they will lose contact and n will be 0. What if the surface is rough? Now let's say it is rough and both of them have started sliding down. Both have got coefficient of friction mu and mu. Both the pairs of surface have got a coefficient of friction mu, and let us say they are moving down. If they are moving down, then we can do the same thing here. There would be an extra force of friction acting in the upward direction. What is that equal to? F1, because we are saying it is sliding down, F1 would be mu1 into n1. So that is mu1 into m1g cos theta. So F1 is going to act like this. Similarly, F2 will act like this. F2 will be mu2 m2g cos theta. And let's say they are accelerating, having a common acceleration A. Why we are saying they are common acceleration A? Because we are assuming that they are in contact, and therefore both must have the same acceleration. If they are not in contact, then we can say that the accelerations are maybe different, but this is how we have it. Now, so therefore you have m1g sine theta, I am writing the fourth equation, plus n minus f1. Minus f1 is nothing but minus mu1 m1g cos theta is equal to m1a, and for the other one m2g sin theta minus n minus mu2 m2g cos theta is equal to m2a. If I add these two again, what do I? Not mu2, this is mu1. This is mu1, coefficient of friction mu rather. There is no mu1. We will take that case also where this is mu1 and this is mu2. Right now both of them are same mu. So I will take mu, and if you add them again, n is going to cancel. I will have m1 plus m2 into g sine theta minus m1 plus m2 into mu g cos theta is equal to m1 plus m2 into a. So m1 plus m2 cancels throughout, and I get a is equals g sine theta minus mu g cos theta. A is equals mu sine g sine theta minus mu. Now if I substitute that here, if I substitute this a here, I will have m1g sine theta on the right hand side, which will cancel here with this on the left, and I will have minus m1 mu g cos theta, which will again cancel with this, and again I will get n equal to 0. So there is no contact force between the two, even if both of them, even if the surface is rough. So whether it is smooth or rough, there is no contact force between the two blocks M1 and M2. Now comes an interesting case where you have mu1 and mu2. The coefficient of friction are mu1 and mu2. Now let us see what happens. So F1 will be mu1, F1 will be mu1 and mg cos theta. F2 will be mu2 m2g cos theta. So if you put that now, I will put it as mu1 and mu2. Yes, I will put that as mu1 and mu2. And you have m1 and m2. Now m1 plus m2, you cannot have it as common. Yes, you cannot have it as common. Now we will analyze this in a slightly different way. What we are going to see here is that we saw in the previous case where it was mu, we saw that the acceleration a1 for this, we had said it was a common acceleration a because they were in contact. Now a1 would be g sine theta minus mu1 g cos theta. A2 would be g sine theta, that is we independently take it without their contact. Supposing without contact, let's say you have left them separately. So their acceleration is going to be mu2 g cos theta. Now you see, now there are two cases where mu1 is less than mu2. That is, this under m2 the surface is rougher. So it will have a lesser acceleration. If mu2 is greater than mu1, a2 will be less than a1. So m2 will trail m1. There will be no contact force. N will be 0. And if mu1 is greater than mu2, the acceleration of m1 will be slower and m2 which is there will be faster, so they will make contact, and hence they will, here a2 is less than a1, and we also can say that a2 not equal to a1. Yes. In the second case, when mu1 is greater, it will be slower, we said, and m2 will be faster and it will make contact. You have a1 equal to a2 equal to a. That is the case. So now there will be a certain contact force between the two, and we can easily find that. So if you write that, what will be the equations now? So we have to write the equation only for the case where mu1 is greater than mu2. So what will be the equation? m1g sine theta plus n minus f1 is mu1 m1g cos theta is equal to m1a, and for the other one it will be m2g sine theta minus n minus mu2 m2g cos theta is equal to m2a. So there are two equations and two unknowns. What are the two unknowns? N and a. We can solve for them. Now in this case n will not be 0. There will be a contact force. Having understood this, now see, in all these cases that we saw, the two surfaces in contact were planar. But we come across several situations where the two surfaces in contact are not plane. Then the question is, how do we do it? For instance, we can have a floor and a wall and a ladder resting like that. There is a ladder resting like that. Now we want to draw the normal force. The ladder is making a point contact here. There is a point here, point. The two surfaces in contact are not planar, but at least one surface is planar. So, for the ladder, when we draw the free body diagram, or for the floor, let's see the floor. For the floor, there will be one N1 normal to the floor. On the wall, there will be a pushing force N2 by the ladder. So by Newton's third law, now I can write for the ladder, I can indicate for the ladder, N2 will be like this and N1 will be like this. This is the normal force on the ladder. How did we do it? For a point, you will not be able to draw a normal. Yes, but for a plane surface, you can draw it, and that's how you do it. Supposing you have another example. Let us say there is a wall here and there is a sphere and there is an object like that placed on it. Now again, this is not a plane surface, it is a spherical. But I know the normal force has to be normal to this surface. So for this surface, I will have N1 like this, and there will be an N1 on the sphere. It should pass through the center. Only then it has to be the radius. Only then it can be normal. On the wall here, there would be a push by the sphere N2. So there would be N2 here, equal and opposite. This is plane. There are 2 point contacts now. Point contact on the sphere and point. I am not shown it properly. I'll redraw that for you. It's a point actually, tangent. The tangent is making a point contact. Point contact here. So here at this point, there will be a normal force N3, and for this rod, there will be an N3 like this at the point contact, and here at the floor, again there will be an N4. These would be the normal forces. Supposing you had, let us say, 2 spheres inside a cylinder. It's a cylindrical vessel, and I have a spherical object and another spherical object. I want to draw the normal force for these. So, for the cylinder, if I take the cylinder, there will be a normal force N1 here, N2 here, and N3 here by the 2 spheres. Now for the sphere, for this sphere, there will be an N1 pushing force. The floor of the cylinder pushes, passing through this. N2 would be like this again, passing through this. Then there will be a weight. I am not showing the weight because we are marking only the normal forces. There will be a contact force. This is a point contact here. So the normal will pass through the center. For this one again, there will be a normal N3 which passes through the center. Okay. That is all. And this is not N3. We will call this as N4. N3 we already marked it here. So we will call it as N4. N4. And there will be an N3 like that. So those are the normal forces. Similarly, we can think of a situation where there is a valley like that and there is a sphere. So there is a valley and a sphere. The force on the sphere, normal force on the sphere would be like this and like this, N1 and N2. On the valley, if you want, there will be a pushing force N1 by the thing and N2. That's how it is. Then we can have another situation where you have a shell, a spherical shell. It is a spherical shell and there is a rod placed on it inside like that. You want the normal force. So on the sphere, you take the sphere. So this rod will push it, so there will be a normal force on the, I'll show it as a separate diagram. Only the, let me show you. This is the shell, spherical shell. So at the point of contact there will be a pushing force, so that will be N1. Here at this point again, this is the rod is here. So here there will be a pushing force again. It will pass through the center, this will be N2, and on the rod, this is the rod, on the rod there will be a force N1 like this and N2 like this. Yes, this angle if it is theta 1 and this is theta 2, this will be theta 1 and theta 2. Now, usually in the case of collisions, we need to identify the normal force. So, let us see some cases of collisions. Supposing there is a billiard ball striking another billiard ball. Well, in that case the two spheres are of the same size, let us say. So, if this comes and strikes this, let's say this is at rest, then the force on this would be N like this and on this would be N like this. It would pass through the center. It would pass through the center. But supposing there is a big ball striking a small ball, then how would the force be? The force would be again normal, pointing. In all these cases we are showing there is no friction, so we are showing only the normal force. And because friction is a tangential force, okay, so we are not showing that, and there will be N like this. That is how it will be. Suppose you have a spherical object and there is a point object coming and striking it. Let's say a bullet is being shot. So when it comes and hits here, now this is a point and a sphere. When you have a situation like this, for a point, you cannot draw the normal force. But you can draw it for the sphere. So for the sphere, there will be a force like this passing through the center. So by Newton's third law for the point, there will be a normal force like that, opposite to this. This is a bullet B. For the bullet, there will be a force like that. Now, interesting thing is, if there are 2 point objects colliding, then you cannot say if there are neutrons, for instance, colliding with in a nuclear reaction, there is a neutron colliding with a uranium atom or something. Well, they are very tiny, small. So the force for such point object can be in any direction. The pair of normal forces can be in any direction. You cannot identify them. If both are point, the normal force can be in any direction. Thank you.